Well, it's that time of night again, Sunday night, 6 p.m. Welcome to Steve's Place. Tonight's guest will be Bill Alek, and he'll be introducing us to the world of free energy and showing us how Tom Bearden's device should work. But in the meantime, let me give a reminder that people can now join the Tesla Tech YouTube channel and have unlimited access to many of the videos we're putting up there. This month we should be putting up almost 300 videos for exclusive members only. It covers the global science conferences, the Tesla Tech conferences, and the exotic research conferences. So consider supporting us. $9.99 a month. The exclusive membership gives you global access 24/7 wherever YouTube is. And I want to remind everyone that the conference is coming up August 10th to 14th at the Crown Plaza. Please contact the hotel and make a room reservation as soon as you can. Rooms start at $82 a night. Includes a breakfast. We're going to have a buffet there, so you can go get up in the morning and run down, grab your breakfast, and shoot on over to the studio or the room there, the meeting room. And I expect we're going to have a great conference. I just got back from Albuquerque, and they're all pretty excited about having us there and everything. For those who haven't been there, it's a great hotel. It's a 4-star Crown Plaza. We have a great conference area and 2 swimming pools, 1 indoor, 1 outdoor. We have a great patio, which is where we're going to be eating our breakfast at, and also in the evenings, we have a social hour where you can meet these speakers and enjoy a bite with them while you're talking to them and learning more about what they have to offer. So get signed up. We have a 30% discount if you sign up before June 30th. Now, tonight's guest is going to be Bill Alek. And hello, Bill. And he'll be speaking on Tesla's on Tom Bearden's Scalar Wave technology. And Bill, I'm going to turn this over to you, okay?
Okay.
So tell us about yourself.
Okay. Well, good evening, everyone. I'm going to speak about Tom Bearden's Scalar Wave technology. And I just want to mention you can go to my website. It's intalek.com, intalek.com. And if you click under the active vacuum link, it'll take you to some Tom Bearden videos. And Tom is, I would say, a pioneer, in free energy, anti-gravity technology. And I went to his conference, way back in I think it was 1997. And ever since then, I've been hooked in the field here. Tom always presents a fascinating lecture, and you'll see that, if you just play his videos, he plays some he brings up some very interesting topics, and we're going to cover that tonight in this lecture. So without further ado here, let's get to the second slide. Now, the fundamental basis of Tom's technology is this Q cross Q. And you find this in Coulomb's law, Q squared. And I remember in college here working with Coulomb's law in some of my physics and engineering courses. And, I never saw this Q cross Q before being applied to Coulomb's law. This is only lately that I've seen it in, on some of the websites here. But this Q cross Q is the fundamental principle behind Tom Bearden's work and the work of many others out there. And I'll touch on that a little later in this lecture. But this Q cross Q, it's 2 opposing vectors. And it brings up this what's called the law of the squares, or the magic boxes. And you'll find that on the internet as well. And recently here, I believe it was last year, a movie was made called Tenet, T-E-N-E-T, and they addressed technology that was not only time forward, which is our universe, but also addressed the issue of time reversal. And Tom spoke quite a bit about time reversal in his lectures. So that's really all part of this kind of technology, because it works down at the quantum level. And this is revolutionary work here. I mean, there's just no doubt about it. Because working with Q cross Q, and Tom mentioned it, and I'll get to it a little later here, but Tom always said in his lectures that matter is very much a part of this Q cross Q principle. So again, I want to emphasize that, I'll get to it a little later here in detail, because I make a very fascinating link with quantum mechanics, okay, quantum field theory. And so let's go to the second slide here. So see, what you want to do is operate Q cross Q in a resonance circuit. And this is where you see this scalar wave emerge out of resonance, okay? And what I'm speaking about here is the transformer coupled to a capacitor. And just looking at that, when you put this on a scope, you can find a fundamental resonant frequency. And at that frequency, the scalar wave emerges out of that. And we'll find out what that's all about here in this lecture as well. Okay, so let's go to the second slide. Okay, this is my scalar wave test bench. And it consists of a Tektronix oscilloscope. And the one you want to get is this 2025B. I believe that's the part number of it. And the reason why you want that one is that you want to work with isolated channels. You don't want to have a scope that has a common ground. You want each channel isolated from the other channel, okay? And that's what this particular scope has. So this is the kind of scope you want to get, an isolated channel oscilloscope. And Tektronix makes probably one of the best. Okay, so in front of that, I have my test apparatus here, which is my transformer. And if you go to my website, intellect.com, you'll see that I have a patent on this transformer. And it's connected to a capacitor. The output of the transformer is connected to a capacitor, and that sets up the resonating circuit. And so the input to the transformer is being driven by this programmable AC-DC power supply. And what you want to do is the AC part of this. And this particular power supply here can run your frequencies within the operating range of this transformer. I believe it's from somewhere around 1 kilohertz all the way down to 40 hertz. So it gives you a very nice range to play with here. And the particular voltage that I'm working at is 8 volts, fairly low voltage. And it sets up a resonance within this network here. Okay, so the input and output, I measure voltages on the input. The current, I use these Tektronix amp probes. You can get those from Tektronix as well. And there's also set up on the input and output. So what I'm doing here is measuring what's called volt amps. Okay, it's as if you hooked up a voltmeter and a current meter, okay, on the input and output side, and what you're going to measure are volt amps. And I want to emphasize that, because what I do with this scope is that it reads the volt amps, and then I read it into some special software that I wrote, and I'll go into some detail about that as well in this lecture. And I'll show you all the mathematical operations that it performs here just by reading the volt amps. And then the scope also determines, it multiplies the volt times the amps, and it gives you what is generally referred to as real power on the scope tracing. And I read that into the software as well. And so from all that, from this information here, I'm able to calculate what the phase shift is between the volts and the amps for the input as well as the output. Now, since we're not applying a load, okay, to the output of this, the only load is the capacitor, the phase shift is always going to be right around 90 degrees, okay, when you read the volt amps. But the volts and amps will be quite high, okay? There's you can do a multiplication on this, which is what I do, and you'll see the volt amps is very high on the output compared to what the input reads. But again, we'll get into that a little later here. Okay, so what you're looking at here in this photo is a test bench. To the left is my laptop computer that runs the software that I wrote. And incidentally, I wrote the software using Visual Basic version 6 that runs on an old XP system that I have running here. And it's a very stable platform. I never had any troubles with writing software, because really all that I'm doing is just interrogating the scope using an RS-232 through a USB port. I'm just reading values from the scope, and the software is performing these calculations. Okay, so this is the test bench setup here. And I call the software Transformer Efficiency Calculator. Okay, so let's go to the next slide. Okay, how to make a scalar wave. This always puzzled me, exactly what Tom Bearden was talking about, in his lectures. And he did go into detail in his early lectures here about what to look for. And he would say things like, any competent lab can do this. Well, it's okay, but what do you do? And Tom, during one lecture, what do I do with this stuff, Tom? And he turned to me one day at one of these conferences. I think it was a psychotronics lecture. He turned to me and he said, don't ever ask me that question again. And I was blown away. It's like, all I'm asking is, how did he make these measurements? And so Tom is quite a character there. So it only took me about 20 years to figure this thing out, what this guy was talking about. But again, he goes into some detail in his lectures, and you kind of have to put the whole thing together, and it takes time to do that. But you can do it. And you begin with this Q cross Q component. Now, if you take this device, but here's the interesting thing about this device. If you take this device and put it on a professor's desk, he's going to be clueless. He's not going to understand what this Q cross Q means, because he's been trained in classical physics. All right? The problem is, and this is what Tom Bearden identified, is that you have to go before the Maxwell equations were simplified by Oliver Heaviside. You have to go before that. And so what Maxwell worked with originally were what are called quaternion equations. And he developed the whole mathematics behind this in quaternion math for doing these kind of calculations. And what's so intriguing about that is that the original equations are the correct interpretation of electromagnetics. It's correct because I see it on the oscilloscope. It's plain as day. You see the scalar wave component that Tom spoke about. But the thing is that in classical physics, when they optimized the electromagnetics, is that they removed the scalar component. Okay, to do the simplification, you throw away the baby out with the bathwater here. You just throw all that away, and you're left with a simplified version of electromagnetics, which is just AC waves. And the problem with that is that when you cannot make the link between these AC waves and gravity, because gravity is more of a scalar function. It has these scalar properties associated with it. But in electromagnetics, there is no scalar components when you analyze it in the classical form. Okay, so we're going to look at that. Now, Tom Bearden said in his lectures, matter is made of trapped electromagnetic energy, which is true. That is true, and I'm going to show that to you. Okay, so let's go to the next slide here. Okay, so how to determine resonance? Well, we just have a resonance circuit. We have the output of this split flux transformer. This is the output stage. And what you see is that we have two output coils, secondary 1 and secondary 2. And they're set up to sum. The voltages sum up, but the current, okay, which produces the flux inside this core material here, is set up in an opposing action. And you have to have this opposing action if you're going to do scalar wave technology. You have to have this. And we know other researchers like Nikola Tesla, Stanley Myers, a few others, set up opposing flux action in their devices. And this is what gets you the scalar function. This is what you need to do gravitational connections here with this. Because really you can do gravity. It's my understanding, according to Tom, that you can do gravity with the original quaternion mathematics that Maxwell had because of that scalar component. Okay, so I mentioned before that on my test bench I have this programmable AC-DC supply, and it's set up to deliver an AC power signal to the transformer. And when you get this resonance circuitry here running, you'll find out that the point of resonance, okay, with the capacitor and the inductance, okay, of this the split flux transformer here has a resonating point, okay, and you can find that very easily, okay, using this programmable power supply. And so when you're at this resonant point, you're with minimum input current that drives this whole system here. Okay, minimum input current is your point of resonance. Okay, so let's go to the next slide. All right, now Tom likes to use this something called a pumped phase conjugate mirror. And it's like, what is that? And this is what happens when you set up a pumping system in this secondary side of this transformer, because what you have is a converging flux path, okay, in your material. And the convergence is produced by these two output coils. And ideally, you would want these coils to be balanced, okay, as close as possible. So you got to be able to tweak the inductance level on these coils such that they perfectly match. But for the sake of discussion here, I'm just using my output coil arrangement here. Now, Tom, he spoke about this pump phase conjugate, and this phenomenon occurs when you have this pumping action going on, okay, in this in the output section here. Now, back in December of 2020, I filed a patent on this as well. And of course, Tom Bearden lectured on this subject quite a bit back in the late 1990s, early 2000s. And it's called this Pcm Resonator, okay? But he didn't really tell you how to really do this, okay? It's like Tom Bearden's trade secret, okay? And he shared it with John Bedini. Those two worked together. And back in the 80s is when Floyd Sweet had a device similar to this as well, okay? So let's go to the next slide here. And this is really from a slide that Tom Bearden presented, that you set up these converging waves, wave 1 and wave 2. And of course, this is my output coils. And the input is really driven by the input side here. And so the output is where you get this, what Tom referred to as a phase conjugate. It's a time reversed wave. And this phenomena, it's an electromagnetic phenomena that occurs mainly in optics. You'll find this arrangement in optics. Now you also find it here, okay, with this colliding, converging waves. And it produces this scalar function, okay? And we'll get to that here as well. And the way that I look at it, the question is it a phase conjugate or is it just a reactive wave? Which is a good question. Okay, Pcm Resonator is the Pcm wave function. And according to Tom, it produces a time reverse replica wave. And this would be, I observed this on the input side of the transformer, but you also get it occurring on the output as well. Okay, so let's go to the next slide here. Okay, examples of Pcm resonators. Nikola Tesla and his magnifying transmitter, he used converging flux, in his transformer device. The Floyd Sweet device used it as well. Stanley Myers, his water car, very good example of it. It's in Stanley Myers patents. You can find that on the internet as well. In my split flux transformer, set up the convergence. And you also find this in metamaterial resonators. There's another researcher by the name of, I think it's David Paris. He gave a lecture on APEC a couple of weeks ago. And this is where he sets up his wave patterns that converge in his metamaterial, which is just, they're just circuit boards with a pattern where it sets up a resonance in this pattern of converging fields. And I know John Hutchison use this technology as well. John, you can find that on the internet, John Hutchison, levitated a 90-pound bowling ball. I mean, that's just absolutely amazing. Okay, this levitation of very heavy objects just using these converging wave patterns. Okay, so let's go on to the next slide here. Okay, now you'll find this video. I was just watching it the other day, and I'm looking at his equations here, and I said, oh my God, there it is. There's the scalar wave. There's a scalar wave in quantum field theory. And I was just stunned to see this. And where you find this is that this is towards the end of this lecture this fellow gave. You can look up relativistic quantum field theory, find the YouTube version, and just watch it. Okay? And towards the end of the lecture, he's asking the question, what is a particle? What is it? And of course, Tom Bearden always said that, well, matter is just trapped electromagnetic energy. And so here it is. Here is the scalar wave component. You'll see that particles with mass, okay, it's very important here. Particles in mass have this function. And if you look at what this is equal to, you'll see a negative 2 pi f min squared. All right. And when I saw that, I said, well, lo and behold, there it is. That's your scalar component. And so what is this? That's your Q cross Q component here. Okay. Because what this frequency is, if you're using sine waves, you're going to have the sine squared term. And this is your scalar wave component. So we'll take a look at what that is here. So yeah, in quantum field theory, you have the scalar wave component, which is critical for creating mass in a particle. And of course, quantum physics, they have to have, well, you got a Higgs field, you got this field, you got that field, and we really can't connect them all together yet, but nevertheless, there it is. And I'm looking at it and said, well, that's a scalar wave term. Okay, that's your Q cross Q component inside this wave equation for particles with mass. And so there's your trapped electromagnetic energy right there. Okay, and massless particles, like photons, well, there is no mass, okay, with a photon. So that side is going to be 0. Okay, so let's go on to the next slide here. Okay, so what is this mathematics that Tom was talking about? Okay, and it's this quaternion, the scalar quaternion solution, which is really the heart of Tom Bearden's scalar wave theory. And so, like I said before, it's based on Q cross Q. And so if you looked at the classical solution to this, you'll discover that there is no scalar component with classical electromagnetics. It's gone. Okay? Q cross Q equals the 0 vector, case closed. So if you put this on any professor's desk, they're not going to know anything about the scalar wave theory that Tom spoke about. You have to go earlier to the quaternion math solution here, which is the original Maxwell electromagnetics. And there it is. There's your scalar component. Okay? And so what you have is a scalar entity. Your Q cross Q equals the scalar entity plus the 0 vector, which is what you have from the reduced classical equation. And so the scalar entity is what we're going to focus on. And so we're using sine waves. So you're going to have sine omega t, all right? And so you let Q equals A times sine omega t, all right? And so when you do your Q cross Q, your cross product, you discover that you have A squared times sine squared times omega t plus the zero vector. Okay, the zero vector is what Tom referred to as your vacuum engine. It's what holds matter together. And so inside this bubble, so to speak, is that you have these two oscillating waves that are counter-rotating with one another, electromagnetic waves counter-rotating, creating the sine squared term. And so what does the sine squared term look like? All right. And this is the fascinating part, because Tom referred to the scalar wave, pump wave, is a local gravitational wave. And so what does he mean by that? So let's go to the next slide here. And so I took these equations and then modeled them using the software called MathCAD. And so I took a sine wave, and then I took a sine squared sine wave. And there's your scalar waveform, which appears at resonance. And so there it is. It has this offset. It's like a DC offset. That is your scalar waveform that Tom is referring to. And so the input into your transformer is going to have your sine function, okay? You're feeding a sine wave voltage, and the transformer is using a sine wave current, okay? But this reflected component that comes back is a scalar wave that is added. It's a current, okay? And this current that's being produced by this transformer is adding to the input side of the current being supplied to the transformer from the power supply. So what you end up with is a sine, let's say this input waveform is the current coming from the power supply, and the current coming from the transformer is your scalar waveform. The two add up, and you get this third waveform that looks like this, okay? The summation of your input sine wave and scalar waveforms, okay? And this is your sine. See, the scalar waveform is your sine squared term, which has this DC offset to it. That's your gravity wave. This is gravity here, okay? This is what gravity waves look like, right here, the scalar waveform. But electromagnetics looks like the top waveform, AC, pure AC. Okay, and so you sum up the two and you get this input plus a scalar waveform. Okay, next slide. And so what do we see on the scope? Well, there it is. Lo and behold, the blue trace that you see here is your input current, which is the sine wave plus the sine squared scalar waveform, okay, coming from this converging waveforms inside the transformer. And it's producing the same pattern. Okay, so if you look at the two here, and there they are. You look at the third waveform here, and the second. It's basically the same type of wave. Okay, so this is what's coming from the split flux transformer, as well as Tom Bearden's device. You know, when he came out with his patent, I think around 2000, 2001, the MEG device, MEG, the MEG device. And so this is what we see. Okay, next slide. Okay, so, you know, how do we analyze these circuits? Because, we're dealing with volt amps, and when you hook up meters, rather than using the oscilloscope, let's say you just had some meters laying around. So you had a voltage meter and a current meter. You would read volts and amps, okay? But the thing is that there's a phase shift associated with these signals because they're AC signals. And it's important to know what that phase shift is, because if you were to drive a load here on the output of this transformer, you can only read real power from a resistor that heats up. You can't read, volt amps, because what's going to happen is that this resistor here is going to force that phase to start to shift to become real, okay, because that's what a resistor dissipates, is real power. It doesn't dissipate what is generally referred to as reactive power, and that's what you get with the volt amps. So what you end up with on the right here is this triangle, okay? So the hypotenuse of this triangle is generally referred to as apparent power, your volt amps. So below that, you have your real power, which is in watts. And then to the right of this triangle, you have the reactive power, okay, which is generally referred to as VARs, VAR. And so the hypotenuse of this triangle here is, of course, the apparent power. And my software figures all that out. Okay, it figures out what phi is, this angle, okay, between the real power and the apparent power. It figures that phase angle out. And I'll show you the math behind that as well. Okay, because when you dissipate power in a resistor, it's going to measure real power, not the apparent power, okay, the real power. And so when you see the input source power and the output load power, there's generally phase shifts in there, okay? And the math is, that's going to be performed here. We'll figure all that out, okay? And so ultimately, we're interested in the efficiency of what this transformer is operating at, okay? That's what we're interested in. So these calculations that you see here, where power equals volts times the amps times the cosine of phi, this is what we're going to figure that out, okay? And then for a resistive load, you can have, there's a couple of ways of figuring that out as well. You can look at the phase angle, or you can just do a simple calculation of V squared over R, okay, which is what we show here as well. Okay, so let's go on. Next slide. Okay, so this is the software that I wrote. It's in Visual Basic, Transformer Efficiency Calculator. It's written in Visual Basic 6, which as I mentioned before, is a very stable software package. And so it performs all these math operations. It gives me the volt amps in and out of the transformer, determines the apparent input power, apparent output power, does a multiplication here of apparent power multiplier here, where it multiplies these volt amps and does a little division calculation. Also, we have there's also power factor that's calculated as well. I don't show that here because it's really, for these type of transformers, the power factor really doesn't mean that much, okay? But it is calculated, and it does print it out here on the screen on the right here. So what we're interested in here is the phase angle, transformer efficiency, with both using the phase angle as well as the load resistor calculation. So we go and figure that out. And we see we have a transformer here that's operating about 90%, which is quite good for a transformer under load. Now, what's so interesting about this split flux transformer is that as you load it down, okay, when you select the load resistor on the output, as you load the transformer down, it becomes more efficient, okay, which is, wait a minute, you know, if I take a conventional transformer, as I load down that transformer, it becomes more inefficient. Well, these type of transformers where you set up this converging pattern here become more efficient as you load them down. And that's what we're seeing here, 90% efficiency. That is pretty good for a transformer, okay, that as you load it down. Okay, so let's go on here. Okay, so transformer efficiency calculator. It's doing all these math operations. And what you see here, it calculates apparent input power, the real input power, reactive power, determines the phase angle, and there's a calculation for that using the arc cosine, some square root operations. It also does the apparent output power, the real output power. It does the whole 9 yards, the proverbial 9 yards here of telling me everything about this transformer. So then it gives me what the apparent power multiplier is and what that efficiency is, the phase of the transformer, input as well as output, what the phase efficiency is of the transformer with an applied load resistor, and what that efficiency is as well. So this is all the math operation that's going on in this the software package that I wrote. And early on here, when I tested using a conventional transformer, that had an efficiency, you know, if you use something just off the shelf, you'll see that that transformer is about maybe between 75 and 80% efficient. Okay, and as you put it under load, it becomes more inefficient. Okay, but these transformers, when you put them under load, the split flux, they become more efficient. Okay, under these loads, which is just the it has just the opposite effect. And I thought that was rather fascinating. Okay, so we covered all the math operations here. Okay, so what this slide shows is a no-load configuration, okay? And I'm operating this transformer, I believe it's at 8 volts, with various loads of capacitance. And what you see is this power multiplier, which is about, you'll see that in the middle of the readout here, which is the apparent power multiplier. We see that under no load, it could be 10 times. And then when you start dropping the capacitance on this, you start lowering, the frequency starts to increase. Okay, so if you start with a high capacitance, 400 microfarads, okay, you see that the input frequency is lowest. And then as you start to drop the load capacitor in value, okay, you start to lower it, the frequency starts going up. But the apparent power multiplier also drops as well here. So I thought that was rather interesting with this type of transformer. So under a no load condition, I'm showing basically what the apparent power multiplier is. Okay. And so that is my lecture. Okay, this is my lecture for this evening. I just wanted to show, what the basics are of using this split flux transformer and showing you what this scalar wave is all about. So what I'll do here is go back to the original slide here where I showed the test bench. Okay, and if you look at the center here, the wave on this scope is that you'll see this sine wave plus the sine squared term. Okay, so it's for real what Tom was speaking about in his lectures about scalar waves. It's for real. I replicated them here. And of course, what Tom says, any competent lab can do this. And so that's what I successfully done here, was replicate Tom's scalar wave theory, okay, that he spoke about in his early lectures here. So, Steve, that's pretty much what I wanted to speak about tonight, is to cover the scalar wave theory. And of course, seeing it in practice here as well.
And you're going to be at the conference this year, right?
I'm hoping to. I might have to do a GoFundMe. Hopefully some people will email me and figure out how to support me to get me at the conference. And I will show this. I will demonstrate, what these scalar waves are, and give a nice demo. Okay, what Tom was doing 20 years ago, in his lectures.
Well, I got to meet Tom way back in '84 at our first Tesla conference in Colorado Springs. And he had a way of lecturing, where you could follow along, and all of a sudden he zips off, and you're on one direction, he's way off the other one. But I loved him. I mean, I think, I love this stuff and everything. I'm a firm believer that a lot of the Bearden stuff is pretty solid. I'm looking forward to the day we can do things, like the Tesla shield he was talking about, which is impermeable barrier to anything. And to be like a silver dome that would cover like a city or something. I know where they could use that right now, but it's not here yet, at least to our knowledge. Yeah. But we have a comment here from Join the Technicians. You might want to comment on that.
Okay, think outside the core where the scalar component of two intersecting zero vectors waves cancel in free space. This compression used. Okay, that sounds like a step number next here for this kind of research. And so to modulate an electric vector field can release extra power. Okay, that sounds very interesting here. Yeah, this is what I'm planning on doing next here, is setting up these multiple scalar components, okay, and seeing what the effect is there as well. Because that's what Tom spoke about, are these converging scalar waves. And so, yeah, this release extra power, yeah, that would be very interesting as well. So that would be a next thing to look at, okay, with this, is to take this to the next level.
Well, I used to have a lot of his, I used to sell a lot of his books, like Fertilance, and he was talking about the scalar weaponry, that he believed the Soviets have. I think if they have it, they're sure concealing it at this point. If they even had it, because a lot of times people claim they have stuff, they really don't have nothing.
Right.
which is why I'm glad to have you at the conference, Bill, because you're a hands-on type of guy,
Uh-huh.
and a lot of the people out here, as you start getting into the scalar fields, the 0 point energy, that uh, you see a lot of smoke, but don't see no real fire there.
Mm-hmm. Yeah, well, I made the connection in this lecture, okay, with quantum field theory, and I noticed that, in this video presentation, that, for ordinary particles, they seem to produce a scalar wave component, and so, they have the sine squared term that also shows up in their mathematics. And I don't think they're even aware of that, okay? Because there's really nothing there in classical physics that tells them what a scalar wave is, okay? You only find that, in the kind of work that we do. So really, we're kind of the people that are leading the parade here.
Here's another question for you.
Could this tech be integrated into commercial EV charging stations? I would say so, because the transformer itself, it's opposite of the performance of a standard transformer. So, in other words, as you draw more power from this type of transformer, it becomes more efficient in its operation. So, in other words, it's going to run cooler, not hotter, like an ordinary transformer would. So it has some very intriguing properties that I think are worth looking into. Okay.
Well, last week I did a show on Tesla's car and my experience with the free energy device. And one of the aspects about it, was that the alternator and the motor was both getting cold, and it was totally opposite of what you'd expect, on our conventional circuits, And this thing should never worked anyway, yeah. And I believe it was drawn. We must have been working strictly with the scalar and the battery itself, because we had a dead battery, to start with. But that battery itself may have been like an interdimensional gateway or something, allowing the transformation of the scalar into the conventional, maybe.
Hmm.
You know.
What car was this?
It wasn't a car; it was my circuits. I'll have to send you a packet later on with a different motor on it. But I mean, this thing was crazy because the battery itself, I thought it was going to blow up, because bubbling away and everything, and when we just changes to it, all of a sudden it went even faster. We'll put a load on it, and you wouldn't expect to see that.
Yeah. Okay.
And here's another comment.
Right. Yeah. Heat is a big issue with this, with the traditional technology. Okay, even with circuit chips, as well. And some of the work that I get into, some quantum tunneling, if you look at tunnel diodes, for example, they have this well, the classical analysis of a tunnel diode is that you have this negative slope associated with it. And they call it negative resistance. But personally, I don't call it negative resistance. I call that negative energy. Okay, you're getting into negative energy. So the part isn't going to run hot in that region. It's going to run cold. Okay, it's not going to heat up, as crazy, as a traditional diode would. So the idea here is to set up, tunnel diodes, and to get them to work perhaps in logic circuits as well. Okay, to not only lower the operating temperature, but it's also increased the speed of the switching, Because one of the problems with tunnel diodes is that if they're not properly compensated, you can get these very ultra high frequency components coming out of it. They can go into this parasitic oscillation at these ultra gigahertz range. So you get these very high frequency parts, in this negative operating region. So that could be a way to speed up switching, okay, in traditional silicon technology or gallium arsenide. It could be a way of speeding up the technology without throwing away, the infrastructure that you built up over the years, okay, to be able to speed up this technology. Okay, cross product place electric longitudinal transmission systems. Yes, Tom spoke about it's like another form of electricity. It's like a longitudinal electricity. I know, I think it's Eric Dollard that speaks about that as well, that you find in electrical transmission systems, okay, longitudinal electricity. And that would be something to look in as well. Personally, I haven't seen anything like that, but I'm continuing with my research as well. And with these phased antenna arrays, because I think David Paris spoke about this as well, but I don't think he really knows what a longitudinal wave is, okay? And so Tom spoke about it, Eric Dollard speaks about it, so it'd be something that's worth trying here to learn more about. Okay, it's a successful space charge separation, the high frequency noise. Okay, if it becomes a nuisance in your electric circuit, it could cause the device to go into this parasitic oscillation, and that's something that you're always trying to avoid. The thing is that what's happening in these quantum diodes, you're getting this quantum tunneling effect. And really all that is really a speeding up of the electron flow. So the electrons are flowing much faster through that circuit, is my understanding of the quantum tunneling. Plus, there's another force that's acting on those electrons as they pass through the potential barrier. It's another right angle force, okay? It's another right angle force that is acting on this, and that could be your longitudinal component, okay, that is acting in quantum tunneling, and that would be something that's worth researching as well.
Well, if there's no other questions, I'd just like to remind everyone to come to our conference. Still have a 30% discount. I know things do cost more out there. We try to keep everybody's expenses to a minimum. We got great hotel rates. We throw some food in the evenings, and we also have a breakfast. Here's another question for you.
Okay, that's where your extra power comes from. Okay, yeah, you need ultra high-speed Schottky rectifiers with the gigahertz range, capture the high frequency power. Yeah, that's something that it's a phenomena that I think occurs in these tunnel diodes, is that the electron flow speeds up, and so if your circuit isn't tuned properly, you can get into this parasitic oscillation mode. and you have to be able to compensate for that. But yeah, that's something to look into. And that's where I think this extra power comes in, is that as you tunnel through the barrier, you have this other force that's acting on your electron flow, but that force is at right angles. Okay. There's a slide in another presentation that I gave that looks into quantum tunneling, and I show where this right angle force acts on the electron flow. Negative resistors, replace internal diodes, replace batteries altogether. Negative resistors, that is a good question for batteries. A good example of a negative resistor that I heard about is to use mercury. Okay. And you probably heard about mercury and some of these other devices, for example, in fluorescent tubes. Because what happens in a fluorescent tube is that you have this avalanche effect that occurs. And many years ago, like 20 years ago, there was some experimentation done. And I think this is shown in some of my earlier lectures, where I show a fluorescent tube and someone hooks it up to a transformer, and they operate it through a diode arrangement, and it can self-charge. It has this self-charging effect because it takes advantage of this negative this negative energy range that you find in fluorescent tubes that contain mercury. Okay, and you probably heard this mercury being used in, let's say the Glocky device, the German Nazi bell. They say that used mercury, and some of these other devices used mercury as well. Is that it exhibits it has a negative energy region where the electron flow is greatly accelerated. In that negative energy region, it's an avalanche effect, and you'll find a description of it in I think Wikipedia. They talk about the avalanche effect associated with mercury. Okay. So what we're looking for is a technology that exhibits the acceleration effect, okay, that occurs with these electrons, or another force that's acting on the electron flow, and we just take advantage of it. And that would be, your over unity technology there, because that's what you need is an extra push that's occurring in the circuit. And I think that's what's happening, with the scalar wave technology as well. Because on my website, what I replicated was the Boyd-Bushman experiment. And what's so interesting about that experiment is that you can take two neodymium magnets, and force them together and epoxy them together. And believe it or not, I applied for a patent on that. I mean, it's such a simple idea, but the thing is that you take two magnets, you force them together, so you have to build a jig, okay, to keep that stable, because the force there it's crazy. It's really scary to work with neodymiums like that. But you got to epoxy them together and then bind them up. And then I replicated the drop test that Boyd-Bushman did when he was at Lockheed. And I found on the internet is that Lockheed took that idea and they incorporated it into a jet plane as some sort of a gravitational modification experiment. I mean, they did take that idea and take it a step further. So Lockheed is working with something like that, where you work with these opposing magnetic forces. Okay, and what that does is that, okay, traditional physics will tell you that you're not really measuring a powerful field anymore. It's like the fields cancel, case closed. Okay, nothing here to look at anymore. But that's not what's really going on, because when you take that magnet that's been forced together and you drop it, it falls at a different rate. Okay, it doesn't fall like, if you set up a test rock. Okay, you take a rock and you take these opposing magnets and you drop them. Now, it's hard to get them to drop at the same time, but nevertheless, if you do, you'll see that the opposing magnet field falls slower than the rock. And I thought that was really fascinating, because you're changing the field energy of those magnets. Okay, and that field energy is interacting with gravity as well. So I think in the end here, what you're really doing is working with changing the gravitational properties of materials using opposing magnetic forces. And that's what you find. That's what I found with the Bell device. If you look at the Bell, the architecture of the Bell device, they're opposing magnetic fields, and that supposedly disentangles the craft from the field around it. Okay, you have this disentanglement occurring. And so, and again, it relates to the scalar field technology as well. And what comes out of that is your sine squared term. Now, of course, with the DC magnet, you don't have any oscillation going on there, but you're dealing with electrons at a very fundamental level. Okay, you're looking at the spin of those electrons. Okay, how those waves are oscillating. Okay, those two waves are oscillating. What makes up an electron are basically two wave functions counter-rotating, and that's what creates your scalar function, and that creates mass. Okay, what comes out of counter-rotating fields is your sine squared term, and that of course creates mass. Okay, so you're fluctuating, we want to fluctuate the mass of this system, modify the mass and how it interacts with gravity. Okay, that's the objective here of this scalar wave technology, is that ultimately we want to build starships, okay, using this type of technology. And of course, conventional physics, they're not going to know anything about this. Okay, because scalar wave, what the hell is a scalar wave? Okay, they're looking for AC waves, where you can't connect AC waves with gravity. You just can't do it. Okay, but you can connect scalar waves. Okay, how we make scalar waves using counter-rotating systems to produce your sine squared term. Okay, and that's how you get into gravity manipulation. So that's my understanding, and how it relates to quantum field theory. It's right there. It's right. The scalar wave is right there, right in front of their face, and they can't see it. So that's your classic physicist right there.
Okay, we have two more comments and then we'll cut it off. Okay, that'll be what's here and what's coming up right behind it.
Okay, we have another question here.
I don't know if it's a question or a comment.
Oh, just a comment? Yeah.
And I have a comment right behind it.
Uh-huh.
Just have a comment.
Surface potentials barely. Okay, that's probably, with the avalanche effect. Okay, that occurs with Mercury. And that's where this, the flow, the avalanche effect is where you accelerate the electron flow. Okay, in your resonator system here.
Well, I guess we'll call it a night, though. And thanks for being here.
Yeah.
And hope to see you there in Albuquerque. I got a room reserved for you.
Yeah, if someone can dig into their pocket here and throw a few bucks this way, Roy and I can sure use it. We can work our way to Albuquerque here. I would love to present and show this technology because the reason why? Because it's for real.
And one more comment: someone wants to know where they can purchase your software.
Oh, the software?
Yes.
I was thinking of making that available as a download. Okay. Yeah, there's a software section there, and I'll probably set it up as a download. And in this lecture, yeah, right there. Go back a little bit.
I was going to say you can just contact you there.
Right. Yeah. Just go to the website. Yeah. I'll probably make it up as a free download, and it works well with the Tektronix scope. It's an old scope, but it works great. Okay. And you don't want a scope that has a common ground at all. You got to have these isolated channels. And that's what this scope is all about. Okay, isolated channel scope. And I just use the ordinary amp meters made by Tektronix to measure the current. You just measure voltages and current, and this thing does all the math, okay, to figure it all out and then presents it in a nice format. There's even a button there that'll take that screen with all the data and send it to the clipboard, okay? And there's some clipboard software out there that can take that clipboard and send it out to a file, and you can build these nice little images, or you can print it out, do whatever you want with it. And it's just a really handy tool. And I finally got that working just in the past couple of months here. I originally had that software for about, I started on it about maybe 4 years ago or so. When I first got the scope, I started working on that software, and I have VB6, on my old XP system here, and the two work great together. I have no problems with it. It compiles very nicely, and it's a very stable piece of software. Okay, and it works great with this Tektronix scope. It takes a little while to read everything in, but if I can get there, I want to get there at the show, and if you show up, I'll show it to you. You can download it and get one of those scopes yourself. So, yeah, it's the way to go.
And with that, we'll see you all next week. Talk to you later.
Okay. Thanks for having me, Steve.